Okay, in this video we'll look at the diagram on page 8 in your textbook, talk through how that might look if you were using a PLC to do closed loop control. We can take a simple example of a temperature being controlled, like perhaps in an oven or any manufacturing process. Breakfast cereal being cooked, for example, or pet food or whatever. But we'll just have a simple oven as our process. And I guess we can start over here at the far left. The set point is what would be input, maybe by the operator. Let's just pick something, let's say 500 degrees. And that might come in right on the screen of a PLC. If we were to put something together in the lab, we would probably just have the touch screen interface and a little text box, and you would have the ability for the operator to type in whatever temperature he wants the oven to run at. So that's known as the set point, input by the operator. Now, if you put in that you want it to run at 500 degrees, hopefully it does. And that's over here. That would be seen over here. The controlled variable, put a question mark there. Is it going to run at 500 degrees? Controlled variable is also known as the process variable. It's really the end goal of this whole setup. So the operator puts in 500 degrees with the intention that the system will run at 500 degrees, that it'll maintain that. The feedback loop is this path here. You're simply going to monitor the process variable, or here I guess the author lists it as the controlled variable. You're going to monitor it somehow, and you're going to use some measurement devices to do that. It's a little confusing, I think, in the diagram. He puts these two almost like they're different things, but maybe if you follow the line back to here, they're the same thing, really. You have your, I'll just put process variable here. Caps. Your process variable is what you're trying to control. Yes, it is the thing you're trying to control. Yes, it's also the thing you're going to measure. I guess you could make an argument that how good's your measurement compared to the actual controlled variable. So what's really there would be here. But what you're seeing with your measurement is here. Gets a little philosophical. How do you know what's here until you measure it? And is your measurement accurate? Can you ever see what's here? Okay. But they're basically the process variable, what you're trying to control. And now you're going to measure it to see what it is. So it's temperature in this case that you're trying to control, and you're going to try to measure the temperature of the oven. That's our manufacturing process. You're going to take your measurement, and you're going to use a temperature sensor, perhaps. You might also have a transmitter, all in this feedback loop that comes along here and heads back to be compared with the set point. And of course, all those things can impact the accuracy of your numbers. Your actual temperature sensor, how accurate is it? And then if it goes to a transmitter, is how well is that calibrated? How well is that calibration maintained? Your feedback signal could be coming back in the form of a 4 to 20 milliamp signal, for example. And that would have originated maybe from a thermocouple, which is millivolts, and then that would be taken from millivolts with a transmitter, it would be converted to 4 to 20 milliamps that represent the millivolts, which represent the temperature. So you can see there's places where you could lose accuracy all along this feedback path, getting it back to the PLC. The process variable ultimately gets compared with the set point for the PLC to be able to make a decision. And in this diagram, I think the author was maybe showing that there might be a separate device here, and then a controller. This would all be more in the context of like a dedicated controller, not so much a PLC. The PLC can handle all this that I put within the dotted lines. And I think you can see that. I mean, it would just be a simple math function block in your program that would take the set point entered by the operator. It would bring that number into the program, and it would compare it to the number it sees coming back from the feedback loop, the process variable. Most likely, if it does come back in the form of a 4 to 20 milliamp signal, that would come in to an A to D converter, and you might have like a 14-bit binary number coming into your PLC, and then you'd also have the entered number by the operator, and the PLC then with a math function can determine if there's a difference between the two. If there's no difference, I mean, if in fact the oven would be at 500 degrees, that would be read back, and the set point and the process variable would match. Nothing needs to be done. The error signal that's generated from that would just be 0, and the controller would send out sort of basically a signal. The controller output signal would represent no change. It would not do anything to the actuator. Nothing needs to change. If the process variable that's coming back is less than the set point, for example, it's 0 degrees maybe at startup. Oh, well, I mean, maybe not 0, room temperature. If we're talking, whatever, Fahrenheit, maybe it's at 70 degrees. So if this process variable is less than the set point, the error signal that's generated is going to be a positive number. And that's going to tell the controller, we need some positive action, we need to do something, and the controller output signal, whether it's an on-off signal, it would basically be turn on in that case, or if it's pulse width modulation signal, it would probably go full blast if you're pretty far away from your set point where you want to be. If you're far away from where you want to be, it might do 100% duty cycle. Or a 4 to 20 milliamp signal, maybe it gives it the full 20 milliamps, telling the actuator that it needs to turn on more, whatever the thing it's turning on more. Turn it on, turn it off, and so on. So if your number coming back was under, that's what would happen. You'd get a positive error signal. The error signal is just the set point minus the process variable. As the oven would heat up, let's say the process variable goes, up to, 510 or something. Now the set point minus the process variable generates an error signal, and you can see it's going to be -10. And the negative error signal would then generate a controller output signal that's going to tell the actuator to back off, to decrease. And it depends on the type of control, and this will be chapter 4, but this, you could have on-off control, which is just a simple, very simple type of control, or you could have some kind of proportional control, pulse width modulation, 4 to 20 milliamps, all these different types of control we'll talk about in Chapter 4. The most basic being on-off. So if your feedback signal is over where you want to be, it's higher than what you want, this negative air signal would turn off, would communicate to the controller, which would send an output signal to the actuator to turn off. If you're under temp, it would just tell it to turn on. So if we had this 10 degrees under, your air signal might come back, positive, and positive air signal is going to communicate to the controller, and the controller will, in this case, if it was simple on-off control, it would tell it to turn on. So these other types, I mean, like I say, we'll get to those, but I guess I could mention, you can probably guess and see that the farther away you are from the set point, like if the process variable is really far away, you can apply a stronger output signal to the actuator. And as you get close to where you want to be, then the air signal would shrink in size, and in this case, the output signal would get less strong. It would start to back off. Okay. All right. Well, I think we can cover the feedback loop here. And hopefully this helps you in the book to see that the PLC is really taking care of this whole dotted line region. Yeah. And like I said, even though in the book it sort of looks like these are different things, the controlled variable, the measured variable, the feedback signal, those are all essentially the process variable that you're trying to control, trying to measure, trying to get it fed back accurately to the PLC. Well, with the feedback loop in place, that is what we call closed loop control. In other words, you're going to ask it to be 500 degrees. And it's going to, but you're not just going to trust the machine to do that. You're going to be watching it the whole time with this feedback path. Just quickly, we could look at this heater or this oven example. We could follow it through to help you see some of these other elements in a closed loop system. The controller will have a sense of whether things need to increase or decrease. So how does it do that? Well, the thing it's going to control is an actuator. Now, what that could be in our oven example, could be a solid state relay here. It could be a phase controller, sort of like what you did at the end of the first year, if you remember. But these would be ways to try to adjust how much power gets to the heating element, if that's what we were using for our oven. So your source of energy or fuel could be anything from 120 volts AC all the way up to maybe 480 volts AC. It could be single phase, could be three phase. That's your energy source up here. And then your solid state relay could do what's called time proportioning. It could turn on and off. Well, for on-off control, it would just either turn it on until it gets to the temperature you want, then it would turn it off. When it falls below the temperature that you're looking to have, it would turn back on, and so on. So on-off control, but you can also, with solid-state relays, you could also turn it on for a certain amount of time and turn it off for a certain amount of time. If it's a slow responding system, I mean, you might have a large oven and just time proportion for heat control, such as how many seconds is it on and how many seconds is it off, So a phase controller would be more precise control. getting them right down to the sine wave, you know, to give a certain amount of the sine wave for each cycle. But these would be ways, and so it would be some kind of a switching element here, and then the manipulated variable is the wattage, the power that actually then is being applied to the heater. So this manipulated variable, if the actuator is at 100% full throttle, you would get all of the, let's say 240 volts AC if you were looking at that. But you could throttle that back. So the actuator could be either a phase controlled or pulse width modulated to deliver maybe 50% of that power, or 0%. So anywhere from 0 to 100% in this case. I mean, and you could put limits on that. You could say it can vary between 20% and 80%, or whatever you want. But there's your actuator. It's going to create a manipulated variable. In our case, it's the actual wattage that's delivered to the heating element, and then the heating element would sit in here in the oven. As the oven temperature is monitored, feedback loop will be the thing compared, and the controller will call for the actuator to, throttle up or down, call for more or less of the manipulated variable. Also, in your manufacturing process, you can see the author has the disturbances that might be impacting it. Maybe airflow, or maybe a new batch of cereal has come in cold, or maybe just the oven door's open, and so on. So those kinds of things will disrupt the process, and that's some of the challenge. You're trying to maintain 500 degrees, but you have things like disturbances that can impact that process. This arrow that's leaving, I don't know if I love that. I mean, I don't know that you have to think of another thing that's going to. Here again, I might redraw that a little bit, so you can sort of mentally lose that arrow. That controlled variable, like we said, actually it's the process variable inside the oven that you're trying to control, and then you're trying to measure it, and then you're trying to get it fed back so the controller can understand what to do and make good decisions, whether to turn the actuator more on or more off, to throttle the manipulated variable that controls how much power is being given to the heaters. So so maybe do away with that arrow. You could take that controlled variable and push it inside this box, maybe mentally, and maybe I wouldn't even call that a measured variable. I would just say that's just the measurement, the attempt at measuring the process variable. So hopefully that helps. I tried to put the process variable here, here, and here. There you go. It's all those things. So okay, we'll get into a little more into this in chapter 4, and I'll probably try to do some videos on the whole idea of proportional band and gain is one I'll probably work up for us. All right.